started with this slide because it's John Harrison is a Yorkshireman who's always been a bit of an inspiration for Wilson Benesch, because everybody should know about the fact that this Yorkshireman, who was a carpenter, actually solved the problem of longitude and allowed shipping and safe travel across the seas in the 18th century as a result of the work that he did, which was incredible for its time. He actually overcame the problem of moving across the seas with a chronometer that allowed accurate measurement. And doing this at this particular point in time was quite an achievement. And Greenwich is obviously the place where time begins as far as the British were concerned, and at that time, of course, when Harrison solved the problem of longitude, Greenwich was like top of the drawer as far as measurement of time. So we actually took Greenwich Mean Time because we thought that it was very important as far as the development of this product. Not because it took a long time, but because it's all about time when it comes down to the critical components that we've designed. So what I want to try and do is give you a little potted history of the company before I go any further, because as you know, this company's genesis was in a turntable, and we started developing all sorts of different ideas from what was currently available when everybody was saying that the analog world was gone and that it was going to be replaced by CD. And Wilson Benesch came along and put together a plan of action that basically was to try and go against that and say actually it's not. And we actually wrote in a business plan when we went to the government for some funding to help with the research and development. We put in that business plan that vinyl wouldn't disappear, it would go down, but it would come back stronger and be a much more esoteric medium. And lo and behold, everything that we projected nearly 35 years ago has actually come to pass. So I think that's a very interesting little bit of history, which when you look at what we were doing at that time, this is actually what we've got over here, because this is what we called a total system when we developed it, the Wilson Benesch turntable. It's got a carbon fibre rack, it's got a carbon suspension system, a carbon fibre tone arm, a low mass platter system, which is on a suspension obviously, and it's got this little beautiful Pabst motor, which when you compare the size to what we've got now is quite interesting. You'll see that later on. And I did mention a little bit about the fact that we've had a lot of support from grants. In fact, we're the only UK company that's actually applied for and won 15 grants to develop innovative high-risk developments. Obviously not all in analog, but more recently we've won some substantial funding from government. The first project we got was what we call the Mondrian project, and if anybody's watched our video channel, you'll have actually seen some posts which Luke put up some time ago on this development. And this is just to show where we were working. We were working with tessellated titanium back in 2008 with Sheffield University. That's how far back we've been working with this kind of material science. And then we did another development which was a blind alley for the company. We went down an alleyway which was inspired by inspired by the desire to get a low mass platter that was high inertia. And we worked with a company that was developing magnetic drives. And as you can see here, if I rotate this, you can see the ratio here. When I rotate it this way, you can see it's completely reversed. So there's no cogs in this. This is all magnetically linked. And what we tried to do with the turntable was to do the same thing. But you'll notice almost immediately what the problem is here. There's no way that that's going to be ripple free or cog free in its functionality. So although we spent a lot of time developing this, it actually didn't go to the end course. But what we did get was a Rolls-Royce software system that developed this outer stator, and that and the bearing went forward into the next development phase. Well, we got the power supply as well, I forgot to mention that. We went to the next development phase, which was funded by government to the tune of 356,000. This was just for a 6-month project, which allowed us to develop the motor drive and the motor itself. And this was a consortium which we call the GMT consortium, which was comprised of Cass Audio and Sheffield Hallam University, a number of doctors and professors, but these were the key ones that were involved in the GMT consortium. Obviously we had access to the whole of the facilities of not just Sheffield Hallam University to do this work, but also Sheffield University to develop this work as well. Michael, how are you doing? Now, just to give you a glimpse of where we were and where we've come to, this is the PAPS motor that was in the Wilson Benesch turntable, and I think you can see there's a significant difference between what that is and what we've now got in the GMT. And what I'd like to do now is just touch upon, for a very brief period of time, some of the work that was accomplished during this. Obviously, one of the key things about any system is that it's got to be developed and passed by CE to pass CB so that it can be sold globally. And if you're developing something from scratch, you've got to have the facility to be able to have this fully tested. And we've already now proven that the system is passed all those tests with flying colours. We're well below the threshold, as you can see here. We've got to be below this for EMC. So we know that we've got now a saleable product, we can put it on the market, and it's passed those certification points. Sorry. So this is just one of the examples of one of the iterations, and when you look at this, the stator and the rotor interactions in a synchronous motor, there's all sorts of variables that you can change. And in this one we've got a steel rotor with actual sections that are profiled. We've got neodymium, which is profiled also, and this is the kind of level of detail that had to be going to by Sheffield University in all their different models before we even started making these things. And when we started making them, of course, we had to make a number of different versions, and we therefore created prototypes that enabled us not only to analyze and look at these systems, measure them and develop them further and then iteratively move forward, but we looked at all sorts of different variables, and we also found where the weaknesses were. And one of the biggest problems that we found was the coil. Here you can see a coil winding device which allowed us to produce this kind of level of accuracy in the coils, for example. So you can see here a skewed magnet coil. This one's a square one and another square one on that side. And it's only when you can get this level of packing ratio and accuracy in the coil that you can actually achieve the level of accuracy that you require when you've got 21 poles in a synchronous motor. If you don't wind those coil windings absolutely precisely, every single one of them, you never get that level of accuracy in the winding. Here is an example of one of the iterations. This is not actually the one that is in production. This is a skewed coil type. And this is one where we've got skewed magnets. So we've not only looked at skewing in the magnetic field of the neodymium, we've looked at it in the coils as well. And all these different variables have been looked at. And for the whole raft of reasons, the one that we've selected is the best one in terms of production reliability and quality of performance. This is the stator, which is machined from a solid billet of Delrin. So I can actually hand this round if you want to just see what's involved in that. That's just to hold the coils, because obviously the precision mounting of the coils and its location on the center of the motor is critical to the accuracy of the drive. Any deviation in the field strength immediately translates into variations in drive. Now this piece of research was all to do with a small band of copper which is within the flux field. And you can see there's a gradual improvement in the quality of the stability of the drive. And what's happening here is that the copper ring that's in the flux is being subject to eddy currents only when it changes speed, however. So when the motor is running perfectly stable, there are no eddy currents in the copper ring, but the slightest change that takes place results in eddy currents being generated that oppose instantaneously any change. So you've got a mechanical system operating here within the design that actually mitigates and stops any variation. This is just showing the assembly that's required to make just one iteration. So you can see the huge amount of work that has to be done just to be able to begin to look at how something works. Here you've got a breakdown of the final design that was selected. This is the copper ring I was referring to earlier. It's only 2 millimeters thick. This is the steel ring of the stator, which is 456 millimeters diameter. And then the bearing is a phosphor-bronze bearing with a tungsten carbide shaft, which is precision machined, ground, and then measured at the university for us, so that we can get the phosphor bronze matched to the tungsten carbide, and we use a stylus to actually read the profile of the surface grinding on the tungsten carbide, and that allows us to get the tribology as low as the lowest possible viscosity, so that we get the minimum drag on the bearing when it's functioning. Now, a key element in the design is the recognition and the importance of Hertzian forces, and making sure that we've got maximum Hertzian forces in key parts of the design and less Hertzian forces in other parts of the design where it's not required. And in the bearing, we wanted to have the contact surface of the single point such that we were controlling it enough to make sure that we never stress the zirconium ball that's at the bottom. So in order to do that, we had to relieve that stress, and we did calculations on the magnetic force required just to take off some of the mass of the platter. It's not a high mass platter, but with the peripheral weights on the 456 diameter, it does add up, and it adds up to a lot when you look at the Hertzian calculations. And this is just a small video just to give you an indication of the freedom of movement. This is not actually powered here, this has just been spun in motion. So you can see there's actually no cogging whatsoever in the system when it's spinning, so even when it's not energized. The torque ripple actually when it's running, as you can see from the, I don't know whether you can see the numbers here, but the torque ripple is down to 0.0013 Newton meters. So that's almost featherweight. Now the tone arm begins with the tone arm that we started with 30 years ago, and this is what it looks like when it comes out of our moulding system that we created over 30 years ago. Only there's a little bit of variation now in this. We actually add raw salt to the internal system, and graphene is in the carbon fibre as well to enhance its damping principally. It doesn't add a lot of strength, the graphene, but it does add a lot of damping. We used nanotubes as well in the past, but as a result of the fact that we can now get a pre-preg which has got a very high accuracy in the mix of the graphene, it actually performs better. It might be worth just feeling the weight of that and the stiffness of it. Now the tone arm development, as all tone arms, apart from the one that Mark did, all tend to have their strength referred back to the ground as a tree grows. Its the largest diameter, as you imagine it, is at the base. Much the same as they do in crane structures, and much the same as we found in the finite element analysis that we did when that tone arm was developed 30 years ago. Here the analysis shows that with a straight tube you've got much higher stress patterns here towards the pivot point, and therefore by changing the diameter of the tube you immediately eliminate those stress points, which obviously when it translates into the transfer of energy, you've got much higher stiffness here with only adding a small amount of additional mass and increase. Well, out. That's one of the earlier iterations of the tone arm. This was one of the first ones that we produced to move forward. And there's the old beautiful Eiffel Tower, which exemplifies exactly what I was just describing. Now the tone arm was just a concept until it went to the drawing stage, and these are some of the sketches that were done to try and to develop the idea of the pivot and the way that the actuator would function, that is going to allow us to move the VTA from a remote control. And it was these sketches and this little wax model that was taken to the AMRC. Now the AMRC is the Advanced Manufacturing Research Centre in Sheffield, which is a large development of engineering expertise, which is designed to accelerate and develop new products. And this is the 4-man team that helped develop that piece of titanium that's moving around the room now. There are some more bits and pieces here which George is going to have a chat about shortly, but I'll hand these around as well because they're worth looking at. And this is actually part and parcel of what was developed initially by these 4 gentlemen who are very clever people that work at the AMRC. One of them's a doctor and the other 3 are quite highly qualified engineers in the field of science of using and exploiting the software and engineering principles that are behind this design. And as I was going to say, I'm not going to go back because I'll just get confused, but I was going to say the bone structure there was one of the things that was important to refer to. When George is telling you about this, he'll explain all this about the tessellations and the various mass that we have in this tone arm. So I'm going to hand over now to a very important member of the team, George.
Thanks, Craig.
Who's been involved in a lot of the redefining of this particular technology.
Yeah, so what the titanium additive manufacturers really allowed us to do is to create an impossible geometry. A weight that's impossible, a shape that's impossible, and an internal structure that is impossible to manufacture by any other means. So what that means is that moving from the front to the back of the tone arm, we have a part here which is entirely hollow. And then we come across this next part, and this is semi-hollow, so this has the lattice structure on the inside. And then as we come towards the rear of the tone arm, we've got the counterbalance here, which has powder integrated into the structure. So that integrated particle damping, adds to the damping. It's kind of like ringing a bell as opposed to ringing a sandbag, which one's quieter. And we also have particle damping integrated into this part here. So titanium itself is incredibly stiff, incredibly hard, and has less density than steel. And now, that lattice structure, sorry if you...
Sorry. I can't get it back.
Can I?
You do it on the
Side.
You got it.
Now that lattice structure mimics what happens in nature. So that biomimicry is what happens when you have bones and ossification inside of your bones. So areas where you would receive higher stress, such as in your joints, that'll have a thicker, denser lattice inside, and areas that receive less stress receive least dense lattice. Next.
Interrupted by.
I ruined it now. So the way that these parts are manufactured is by a laser coming across a bed of powder and physically melting the titanium powder itself. Titanium's got a very high melting point. This is an incredibly powerful laser. And that melts the powder, which is then removed and extracted by hand here. And that powder is entirely recycled, because titanium is a very energy intense metal to make. It's a bit like an archaeological dig, just pulling away the sand to extract the artifacts underneath. And
That's that piece.
yeah, I'll hand this around. So that's the pieces that you see there. And that's the finished product. And I'll hand it back to Craig, who can tell you about the rest of it.
So essentially what you're seeing there is a table full of components which have just literally grown from the powder. So from a manufacturing point of view, it's a very efficient, very relatively low cost manufacturing technique. It costs a lot of money obviously to do, but if you were to try to do that any other way with a milling machine, it would be obviously, as George has just pointed out, completely impossible to achieve. We've got basically, if nature was to grow a tone arm, it would look like what it looks like. Now we come to the subject of VTA, and for VTA we have had for a very long time, the standard procedure is that you adjust the VTA with a screw thread. If you're lucky, you've got 40 TPI to adjust it, and if you are extremely lucky, you've got it right in front of the listening position so that you can evaluate the way it's impacting upon the stereo image. But of course, that's not something everybody has, or does somebody have that? I don't know. Maybe. But what we've got to do is try and get rid of that if we can. So one of the things that we have exploited in order to get rid of that is a piece of equipment that's taken straight from our machine shop. In fact, this is a chuck that was patented about 5 years ago, and essentially what it does is it allows the shaft of the tone arm to be moved in the y-axis with accuracy of a nanometer, and it does that by virtue of hydraulics. Now, because of the precision of the chuck, this is actually a promotion video for the machine shop world. So the chuck is designed to hold a machine tool to extraordinary accuracy and repeatable accuracy as well. But the beauty of it is, for the VTA adjustment, is that it allows that shaft to move very accurately when the VTA is wanting to be adjusted. Now, typically what you would find with most VTA adjustments is that you have to undo a thread, and then the system is unlocked and you don't know how, where, what, or what you're doing. With this system, you've got complete control over the central axis of that y-axis when the adjustment's being made. So as you can see, they're dialing in here a very high level of accuracy. So what we've done is just basically taken a tried and proven technology and adapted it for our own purpose. So you can imagine now, if you can get that level of accuracy, it means that the positioning of the central spindle of the bearing of the record player can be precisely dialed in to the central shaft of the tone arm to levels of accuracy that aren't that easy to achieve any other way. And of course, when it's clamped, you've got the hydraulic pressures that transfer any energy from the tone arm into the rest of the chassis of the system. So, the other thing that is important that we've got to recognise is that we have to make that adjustment to the tone arm. And for that, again, we've gone to another industry. Only this industry is in space exploration using optical telescopes, because if you can imagine trying to view something that's 1 billion light years away, you only have to move a very small amount before you're 1 million light years away, almost within a fraction. And if you want to get back to that point and you want to then track it and trace it, the only way you can do that is with nanometer precision instrumentation. So what we have done is we've taken this technology from this particular field of science, and we've transferred it into the VTA adjustment system of the tone arm. Oh no, you can't see that yet. No, that's spoiled everything.
That's me.
No, nobody saw that. It's not in your mind. It's not going to play this video. I don't know why. Oh, here we go. It's just the internet's taking a bit of time. Play. It's really exciting. It's worth waiting for. Is it going to play? If it doesn't, I can do it with my fingers. Basically what this does is, you can see these are piezo ceramic legs. and this is the shaft that actually moves. And what happens is basically when you operate the piezo, those legs flex, and they flex by a 1 nanometer, repeatable. And that's the big word that's important with this. It's repeatable. So if you have a position where you've set your tone arm and you want to get back to where that was, all you have to do is press a button on the remote control in your seating position, and you can take it back using this piezo device. That's showing you how it works. So at any point in time it's locked. It's never able to move the shaft. It will always stay fixed. So if you stop moving, it's always held. And you can make this thing move really fast if you want to do. If you've heard derailleurs on bikes with electric derailleurs, you can hear them go zzz, 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 when they change gears. It's exactly the same technology, so you can understand it's very reliable if it's being used on a push bike that's doing the Tour de France. Oh, what's happening there? Tech. So we're using that now to be able to allow us to work with that chuck to be able to make micro adjustments. And that means that we can do away with the human, because the human is the problem. Because we don't have spare humans whilst we're listening to music who can do the VTA adjustment for us whilst we're listening to the system. And invariably the record player is normally at the side of the room. And so if we can get rid of this guy, everything's good in the wood. I don't know who this guy is, but anyway, something awesome.
I don't want to know who that guy is.
He predicted vinyl was coming back. He's predicted David is coming back too.
I just found him on the internet. I just thought I'd put him in.
I still got my hair. That's it.
That's a bit below the belt. So what we're doing here is showing that we do this by a remote control system. So the remote control is a local area network. It allows us to put the speed in that we want, start it, stop it. We can lift the tone arm, we can drop the tone arm, and we can adjust the VTA, which of course are facilities which aren't commonly associated with record players today, and which enable a whole way of listening to music which isn't previously possible. And not only that, we'll come on to some other benefits of this in the next slide, because the bearing of the tone arm is the thing I want to talk about next. The bearing was developed like the tone arm itself. The carbon tube was developed 30 years ago, and it's based on the principle of a kinematic location. So you've got 3 balls. It's the same as on the base of the speakers, so if you're familiar with it. And then there's a 4th ball which locates in the top. And we've got a steel ball here and 3 zirconium ones in this design. So at the contact points here, what we are legislating is there's going to be enormous pressure because these are tiny 1mm balls. So you end up with a contact area of 0.003. And that means that you end up with very, very high pressure points. And why is that important? Well, what you're trying to do with a tone arm, if anybody's got one, I'd appreciate it if you've got a tone arm, anybody? Oh, there's one here. There's one here. Got one. So what you're trying to do with a tone arm, obviously, here we've got a wand that's been removed from, is you're trying to control energy. What we're doing with record players is basically we've got a lot of energy that we're trying to control within the system, which we don't want to get back to the reading stylus. So the energy that comes into this system, as soon as it gets into here, we've got to try and deal with it. We don't just ignore it. So with the carbon fibre, obviously we're into a good start. And what we've got then is to try and make this first area that we see here as strong as possible. Because if you can elevate this region to the highest possible resonance point, then that's going to reduce the burden on the rest of the system. So again, we're using tessellated titanium here, which creates a very strong eye section with the carbon fibre, which is 5mm thick at the end of here. And then we're using, if we want to do, we don't have to do, but we also have a fin, and this creates a sphere of structural integrity that's enormously stiff and also quite low mass for the quality of the stiffness that you're getting. In fact, you can have a look at them if you want. So this is going to be the point where we're trying to kill as much energy as possible. Now the helix of carbon that is down the tube now comes to this section, which is now a composite. This is a raw cell section. So internally in here we have a raw cell section which is defeating a lot of the energy as a result of the stiffness and damping it's introducing. And then also then we go into, like George has pointed out, a hollow section, a tessellated section, and a solid section. So what we're trying to do is then get any energy that's coming into here to that single point bearing there, where then we've got those high pressures that I've just referred to of 170,000 psi. So that's almost as though it's a solid, but it's a solid that is reliable because of the fact that we're using these 1mm balls. If it was a unipivot, what you would have with a unipivot is essentially what if the Hertzian force is on here, if I want to do, I can stick it straight into the core, because all the energy all the force that I'm applying is going to a tiny little area, and it's the Hertzian forces that we are exploiting here to get that energy transfer function that we need in the tone arm. But the other beautiful thing about this design is that it also means that we can take this tone arm off the top of there, put another one on, go back to the seat, dial in the VTA, and we've got a different cartridge, different tone arm setup within a minute.
What's the effective mass of the arm?
We can manage that. We can give you a titanium tone arm.
Yeah.
You can have the fin at the end. We can have different hollow sections. We can have aluminium. So we have a number of different variables. It will be supplied with titanium and aluminium in the first instance, but
So-
there is a large number of variables that we can manipulate in order to get exactly what is required
So
for the
basically,
cartridge.
customers are saying, I've got cartridge X, and you give them a tone arm with a correct effective mass. for
We
that.
can do that. Yeah.
Yeah.
Yeah, yeah. That's something that this kind of technology makes possible with ease.
Yeah.
So the next thing is, after the tone arm, is that all this system needs to be isolated from the world around it when it's functioning. It's the level that does that. Now the level system is a system that was developed again from the optical industry, where if you've got microscopes trying to see something, you've got to isolate the world from the vibrations. So what we found was a system which fitted perfectly with the form function of our motor system, and allowed us to create a level which basically sees two pistons, pneumatic pistons, on either side of the structure of the motor, and that is computer controlled, and it allows the system to be separated from the environment to 1.7 Hertz vertical axis and 6.7 horizontal. It's completely self-controlled. It manages itself, it levels itself. You can have different settings. If you want it to have a nice floppy sort of feel about it, you can have that. If you want a firm feel for shows, so that when people come along and they start banging it around, it doesn't get too disturbed. And those can actually be stored in the computer, so that if you want to change it, you can do. So it allows a lot of flexibility as well. And the level means that we can, when it's mounted onto the rack, which we developed, that rack came out 10 years ago. Just shows how much work we've been doing, because the rack came out long before the record player, but that rack was actually developed for this record player. But with it, when it's with the rack, it means that we've got a lot of control over the environment, so that even if we've got really noisy environments, the rack which we've developed enables the presentation of the turntable so that it's got the minimum amount of energy accessing the system. Now, just to briefly, I'm almost finished. Thank you for your patience and time. I just want to talk a little bit more about the tessellation, a little bit more about the cartridge, because I've only touched upon the structures. I haven't mentioned anything about the cartridge yet. Now, the cartridge has got a couple of things I just want to mention. First of all, the cartridges that we're going to be supplying first with these systems have got three variants in the cantilever. The first variant is ruby, the second one is sapphire, and the third one is boron. It's entirely up to the customer which one they have. The rubber isolation rings here, there are two actually, the rings that are being used on the cantilever. But the most important thing that I want to refer to is the fact that we've now got a hybrid cantilever. It's not made from one material. We've added onto the cantilever in a way that Mark will appreciate, stiffening at the center rather than at the pivot point. Because what we're trying to do is add as much damping but with as low a mass as possible to the cantilever right at the center of its structure. And obviously the reason for that is if you've got, imagine a straw, obviously if you bend a straw, the first thing it's going to try and do is bend in the middle. So if you can stop that happening, you immediately reduce the first resonance. So that's what we've done. We've added a UD carbon tube. It's extremely low mass. It's literally 2.5 millimeters long, and it's right in the center, offset to one side. And the reason we've offset it to one side is to create that asymmetry, which is in this and in the cartridge shell as well, so that you don't get that single resonance that is common in a single asymmetrical design, a single symmetrical design.
What stylus profile is it?
It's a micro ridge,
Supplied by?
a company that we collaborate with. Now finally, the signal that comes from a moving coil system obviously is always going to be something that you want to preserve, look after and protect, because in the world that we live in, the world is full of EMC. So we've produced now a very simple solution to this problem. We've eliminated the need for a big long piece of wire which comes out of the tone arm, because we've placed the tone, if you look at the tone arm, you'll see that the bearing and the wire is almost exactly in line with one another as a result of the fact that we can create this unique geometry. So the wire emerges at the top of the tone arm, and as you can see, its exposure is tiny. There's no 150 millimeter long leads of wire that are all going to get subject to EMF from the outside world. And that then plugs directly into the transformer. So the transformer is here. So you're talking about a distance of this amount before this MC voltage is raised to moving magnet. So that's quite a significant increase, which enables you to get rid of a lot of the major issues of interconnection between the turntable and the phono stage. It's during that first stage of connectivity that the very, very small signals of a moving coil can be degraded. And that's why the stage one is perched as it is directly above the tone arm. Now there's a few other things that I'm not going to spend a lot of time on. We do provide clamping system which is based on an ER16 collet chuck, so that we can keep the mass down but keep the pressure on the record sufficient to hold it. There's a little bit of information here about the R1 rack and the nodes that we developed. This actually was taken to the university, and we put 2 tons on this before it broke on this rack. There are 14 millimeter threaded bars here which create a reinforced concrete type arrangement in the rack. And this is the titanium node that was developed by the AMRC, but we've subsequently redeveloped this and we now use a polymer which we grow internally. And finally, the last slide, which I think is really quite nice, is just some of the people that we have collaborated with on this long development program. It's not going to show that slide, unfortunately. I was really looking forward to doing that. But anyway, there's obviously a lot of people have worked on this. All this expertise, all this intellectual property, and all this knowledge and expertise doesn't reside exclusively in Wilson Benesch. Obviously, we're just capable in terms of certain things. You have to go to universities, you have to go to science parks, you have to go to engineers and all sorts of different people to gather all this information. But I think what we've tried to do with GMT is try to bring something new to the market that obviously has certain strengths that we hope will perhaps show a new direction for where we can go with analog design. There are a lot of very expensive turntables out there, and they're all still very much based upon technologies which have been around for a very long time. And I think that with a new motor, with a new method of holding the tone arm, with new tone arm design, with the new isolation systems, I think we've done something that is really quite different. It's taken us a long time to get here. We should have been here years ago, but we finally got here. So I do appreciate the fact that you've spent so much time here on such a busy show, listening to this presentation. And if anybody wants to ask any questions or listen to the system, we're going to shift all this out of the way now and obviously put some music back on.
Can you change the transformer in there to account for the particular cartridge that you're using with if you don't use your cartridge?
Anything is possible, Michael, yes. Anything is possible. We machine everything. So if somebody wanted a specific design, we could easily machine a different structure. And there is already a design which is looking at different options for the end user that is not provided by this particular option.
What's the base price of it? The starting price, as it were?
What do you think it is?
A lot.
Figure?
I think this is. I think this question might be better answered by Luke.
Yeah.
Is there a dust cover?
No, we did produce it and develop a dust cover. We are looking at a dust cover which can go on top of the stage one, but the stage one eliminated the ability to be able to put it in easily.
Who needs a dust cover? Who showers?
So Luke.
So we've tried to make the pricing as simple as possible at this point, because obviously the turntable is comprised of lots of different discrete systems, if you like. So there's the VTA control, there's the drive, the Omega drive, there's the alpha isolation system. So we're grouping all of that technology as one turntable. We've then got the two tone arms at the moment, the two cartridges, and then of course the rack. So the base price for the turntable is £215,000. The US dollar price is around 302,000. The titanium tone arm, which is the Graviton TI, that's 25,000 UK, 34,000 US. We've got the Graviton AL tone arm, which is aluminium. That is 19,000 UK and 26 US dollar. And we have not yet priced the cartridges because there's still a few bits that we're working around with that. But our first review is basically scheduled for September, and we will have completed that development by that point. You add in the rack, they're 6,000 a level, so 18,000 UK, 26,000 US, so thereabouts. So a total system price is around 277 UK, which.
So that's the most expensive turntable in the world ever.
No, it's half the price.
Is it?
No,
Of the most expensive.
There's a lot
turntable.
more expensive turntable.
Yeah. There are a number of other turntables that are considerably more than that.
Yeah.
So I think we're
This is mid-priced.
we're somewhere between most of the field
Yeah.
and then a few others at the other side. So I think we have something quite compelling. I suppose it's all relative, right?
Yeah.
I think it's a bargain.
Thank you, Mark.
Can we have that on record?
Mark
On our record.
Thank you, Mark.
Serious, the tech in this is just outstanding. No, I mean that.
Thank you. That's very kind of you to say and appreciate it.
Yeah. We'd also like to make a point to thank our partners that have joined us in this room this year. So Dimitris of Ypsilon is here with us in the room today, and the system, I hope you will all agree when you listen in a moment, is superb. We're very, very happy to be partnered with Ypsilon. And we're also supported here today by Crystal Cables as well. So without further ado, we will clear away this presentation.
I'll get my box.